Thanks for the intro. Some people might know me from my former life. I did HPC for Intel for 7, 8 years or so. Recently switched to AI, right? Things are close, and that's something I'm going to talk about today as well. Where is the overlap, and what is it actually good for, and what can we do about it? That's one of my topics today. So, from data to insight, and I focus on AI, but I saw a few things about HPC as well. 3 parts. One, I wanted to look at what we call the business imperative. You can also name it the research imperative. So why are we doing those things and what's behind that? Then I'll look at the AI journey, right, as we call it. So how do you actually put an AI solution together? How do you get from data to insight? And then obviously I'll talk a little bit about our technology as well. So that's the 3 parts. Let's start with the business imperative. So honestly, if you look at how do we get insight, right? We can do modeling and simulation. That's what we know as HPC people for a long, long time, right? Don't need to talk to you about that, right? But then there's data analytics, right? Just looking at data which is produced by things, by persons, by machinery, right? And I can draw conclusions out of that. And then I want to visualize it because we are humans, and if you look just at numbers, it's not that insightful. And last but not least, right, as we bring data together with compute power, we can use technology which actually was developed quite a while back, which we call AI. Remember, I'm not the youngest guy anymore, but I even did AI at university, and that's more than 25 years ago. So why do we do it now? Because we have the data and we have the compute power. So frankly, if we could all do this on the same infrastructure, we would all be happy, right? Because that's what you need to get insight. Agree? Okay, let's see how we can do that. Okay, so what all the fuss about AI, right? I mean, in computer science, we have been looking at data since the inception of computer science because that's what we do, right? And what we usually do is to look at data in hindsight and do some diagnostics, right? That is by far and large still the majority of use today, right, when we look into computer cycles. But what we actually would like to do is to get forward-looking forecasts out of this data we have. Agree? And the last step is actually what we call cognitive analytics. Now, what is that? It's basically, as an example, if you have a machinery which produces parts, and the parts can be good or bad, right, in several ways. I can take pictures of these parts and analyze the pictures fine. I can make a forecast on when this machinery needs maintenance and all of those things. Then you are here, right? But if I want to have really an adaptive act in this machine, that would mean that machine adjusts itself to produce only good parts. And when bad parts come out, it automatically is analyzed why these parts are bad. And whenever anything can be done in the machinery to adjust, it acts and produces good parts, right? That's what we call cognitive analytics. It's just a plain example of that. So what we want is insights, obviously business insights, operational insights. We want insights around security, while whatever we can draw out of data, right? And I don't need to talk about this here, right? There are so many data producers today. And frankly, I think most of that data isn't used today, right? So we're in the right business here when we use AI as a driving force to really get value and insights of this data. That's what it's all about, right? And in a combination, right? Because if I only use AI, I can do so much, a lot, but I use it in combination with simulation. I use it in combination with visualization and traditional analytics. That is actually all the tools I need to get insight out of data. Now, what is AI? We saw a bit more complicated version of that picture before from DK Panda, and I'm happy that we use the same kind of base definition here, so not to confuse you. AI obviously is a lot of different methods, right? Which is the big circle here, if you will. The most known methods, right, are machine learning and deep learning. You can see deep learning as a subset of machine learning. Machine learning basically says I have an algorithm, whatever its form is, which learns from data, which actually programs itself. You can do this in a classic way, which we call classical machine learning, using statistics, using tree algorithm, Bayes' algorithm, and many others. That is the bigger circle here. Or you can use neural networks, which is the basis for what we call deep learning. And on the right side, you probably know this as well, right? There's 2 steps in deep learning, which is training, right? I take a basic topology, which is a set of nodes and vertices, which we call neural network, and I train it, right, with tag data. And then I use this trained network to recognize new data and give me some insight of this data later on. So that's the principle, right? I guess most of you know this already. Actually, who is working with AI technologies today of the audience, one way or the other? Well, not that many, actually. I guess it's going to be more when I'm here next year again, hopefully. Because actually what I also wanted to talk about is a little bit where is the overlap between HPC and AI? A lot of people are speaking about the convergence or overlap or whatever you name it, right? And I wanted to take a little bit of a closer look at that because I think there's 2 things which are really interesting about this overlap between HPC and AI. And even this forum here used to be called HPC Advisory Board, right? It's now called HPC and AI Advisory Board. If you look at the big HPC shows, ISC and SC, there's AI all over the place. So why that? Now, if you look at AI, and if you look at HPC, right, we have the what, right? We know the HPC what is mostly modeling and simulation. That is how we usually define HPC today, right? On AI, it's basically knowledge discovery, as I explained before, in lots of data, right? How can I do this best? And what kind of methods am I using for that? So yes, feature learning, pattern classification, reinforcement learning, neural networks. These are some of these AI methods which we had in this big bubble before, right? So that's how we do it, right? On HPC, HPC has high performance, so we use HPC clusters, we use data parallelism, we use high throughput and bandwidth machines, we have large memory in those machines. We all know that, right? Now, if we want to mix those 2 things, what is happening, right? Let's see. Then we have AI on HPC and HPC on AI. So AI on HPC simply means I use what I have in HPC as a how, right? Basically the machine, the high performance computer, to do what I want to do in AI, right? After all, in AI, I need a lot of performance as well, for training as well as for inference, different ways. But if I have a lot of data, I need a lot of performance to handle that data, learn from it, and inference with it. So that is clear, so I can use it. I can use basically the hardware I have in HPC, and we had examples of that before. I have a few more later on. But on the other hand, what is really interesting as well is HPC on AI, I want to call it, basically. It's also a different overlap between HPC and AI. So what is that? That is if I use the how in AI, the techniques of neural networks, of pattern classification, to make what I usually do in HPC, which is simulation and modeling, better. Now, how does that work, you might ask? I have an example in a second, but from an abstract way, it's basically using data I have from real weather, from real machinery data, and I compare it to what I have in simulation. And I learn from the real data to make the simulation better. There's lots of potential in this. And we are only at the beginning of this, frankly, because today, the most used approach in HPC, in simulation, is the brute force approach, right? So we simulate, and we go down the wrong route. We simulate again until it all works, and also the numerical model matches the reality. How about when we can make this much more intelligent, use the intelligence in artificial intelligence to make this better? That's the idea. And I hope you now understand a little bit better what HPC has to do with AI, right? Because I think many people speak about it, but it's better to understand it one level deeper where the overlap actually is. It's a simplified model, but I hope it works for you. Now, I promised an example. Now, I have the honor to work with CERN in the CERN Open Lab since a long time. Intel does that, and I do this almost 10 years now as well, almost, yeah. And there's really bright researchers in CERN and in the CERN Open Lab. So I thought I'd take one example. Sofia Vallecorsa from the CERN Open Lab is actually behind that, and a number of other researchers. So what they do is a little bit on what I described before. Use some method out of AI, in this case, neural networks, and deep learning, to make their job easier. Now, what is CERN's job? Their job is really to run this. They run with LHC, right? They run experiments with detectors, right? And these detectors measure what the particles do when two other particles collide. Then there's other particles being produced, and they track the particles, right, with what they do, how their load and everything, their masses, and then they try to basically prove theory. And how can you do that? So they compare the reality, which is the data they get from the detector, with the theory, which is basically something you can simulate. So what they do, they run Monte Carlo simulations, right, which are fairly costly, HPC, right, to do exactly that job, to find the truth out of the experimentation, right, and compare it with the theory. This is how they found the Higgs boson, right? And they are doing many other things which are related. It's simplified, right? If anybody from CERN is here, they will probably say it's not that easy, but that's the principle. Now, why should they use something like what we call GANs here? That is an abbreviation for generative adversarial networks. This is basically you train two different neural networks and have them compete with each other, right? And have basically one network which is producing the data, the other is discriminator, then you compare it with reality, and hopefully they get some ground truth out of that. That's the principle, very simplified. If you're interested in that, there's a nice paper from Sophia out and some presentations. And basically what we have done together with them to run this GAN, this 3D GAN, it's a specific subset of a GAN on 128 nodes, so scaling it up on the TAG machine, and really get scaling efficiency, first of all. That is what we as computer scientists are interested in. And what they also get out of it is they can do better science, right? They can do it faster, replace some of this big compute here with an intelligent method. So this is a little bit like HPC on AI, right, if you will, or mixing AI and HPC. One example. I think there's more potential in it. We will see more applications where AI is actually used to make all the simulations run very efficiently and produce the right output, hopefully. The other example I had, you have already heard a lot about, this is PlantNet, which we did with Sines, Jansi, and INRIA together, right? So I don't want to spend a lot of time on that. Again, this was a very scaling example which we ran on a large cluster, so HPC hardware. And if you will, this is my example to run AI on HPC, right? Because this is simple AI, it has nothing to do with simulation or any mix of it. It's just you take an AI workload to train the networks for the plant net to be used on a mobile later on, but you train it on a large machine, right? That's a very good example. And you have seen the background on this already before from Gabriel from CNES. Okay. So I hope this was illustrative in terms of, okay, what are we doing to get inside with AI? How does this relate to traditional HPC, and how can we bring those things together? I think we're actually really in the midst of this, or rather the beginning, if you will, because we will see it around us and helping research and helping production a lot in the future. Now let's look at AI, what we call the AI journey. Here I want to speak a little bit how we actually come to solutions, right, using AI in a, let's say, simplified manner. So if you look at a simple circle of development around AI, we can see a number of things, right? First of all is the challenge, right? What I actually want to do. Then there's a couple of steps on before we reach to technology, which is the thing we like to talk about, and actual data modeling and deployment, which I'll speak a lot about. What are these three steps? Where we actually need to look at the approach, the values we produce, the people we have in this process. Let's look a little bit more in more detail. And actually, the next 2 or 3 slides are based on a practical example. So this is nothing which I just put on a slide because it looks nice, but we actually ran a POC with a real customer around this circle and around a solution, and also how much time some of the steps are taking. So the first 3 steps are having a little bit less to do with the actual technology, right? Brainstorm the opportunities, assess which kind of approach and which kind of machine learning, AI technology is actually the best for that. Here, this is a defect detection example, actually, how you use a camera to detect corrosion, like here, on these bolts with a camera, right? That is the practical example we have been using here, together with a customer. And they obviously choose to use deep learning. Deep learning is very well suited to work on images. That's why they chose this. There's other methods, obviously, on other data which you can choose. Then what many people forget is about the ethical part. It's not that hard here, right? Because the data is not coming from persons, it's just coming from things, right? So it's not that big, but if you use personal data, you really need to think about the ethical aspect and the security aspect of the data, social aspect, and other things. So these are the first 4 steps. Then if you look at the next steps here in terms of the data and modeling, the technology part I'll cover later, as you have seen from my agenda in much more detail. But if you look at the data and the modeling, now this is very important because many people think, okay, here's AI, I need to train a neural network. But what I need to first do before I can train this neural network, what is it? I need to handle a lot of data, right? Because without data, you have no AI. That's why you didn't have it before when I was a student, because we had no data. There was nothing recorded big enough to do anything around AI in practical terms. So what you see here is actual approximate timing on engineering estimates for the time spent in those steps. So sourcing the data, transmitting it from a camera into a data center, do the ingestion, clean up, integrate it, and stage it. So this contains also the labeling of the data, which is very important because you cannot train a neural network so easily if you don't have labeled data. There are methods, obviously, which are a little bit more inventive in this, to not use humans for all the labeling, but you need to label the data to do the training, right? One way or the other. So these are the steps here, right? And you see the time spent in them. And then actually you do the modeling, right? Here the training starts with 30% of this time, then tuning the hyperparameters, testing the inference, and document the results, right? That's a typical loop. And some people think the only thing you need to do with AI is this one. You're wrong, right? And even there, the training is only a part of it. That's the reality, right? And we have seen this in many cases. We have taken one example here of this defect detection, where all the other parts are actually much, much bigger than just running the training, right? We tend to focus on that because we're technologists, we're computer scientists. When something is calculated, we are in. That's why we often focus on this, but the other parts of handling the data, labeling the data, are very, very intensive as well. So just to remind you. And then this is how the deployment looks like in this case. You see it's fairly complicated from a practical perspective. Basically, you have sort of drones taking the pictures and fixed cameras. You do the data ingestion. For the incident part, it goes directly there. For the training, it goes through the media store. All these steps we had before implemented, and then basically do a retraining from time to time. And here you can see basically what kind of hardware you have. You have Movidius VPU core processor in the remote devices. Then you have media servers based on various parts. Here, Xeon 6100 scalable processors, and here on the inference. And interestingly enough, the hardware here is pretty common, right? You see various versions of Xeons. That also means that I can, for instance, repurpose the machines I have used for training for running inference later, and vice versa. I can concentrate my approaches on training with a lot of the machines and move the workload back and forth because it's all based on Xeon in this example. The software stack, TensorFlow, MKL, DNN, and then the OpenVINO toolkit, Movidius SDK. I'll explain later what that means, right? Just wanted to give you an example how it actually looks like in practical terms. So now let's look at the technology we're using, right? What is behind that? What is new? And where are we going with this, right? So if you take a 1,000 or 10,000 meter view, right? What you have is hardware, software, and not to forget community, right? In terms of building a solution, you usually do it not alone. You work with partners. You use resources which are out there. So this is very important, often forgotten, but sometimes more important than just the software and the hardware stack, right? So we'll look at the hardware later on, what we actually need for that. There's a lot of software involved, a lot of open source software, like the deep learning frameworks. And we're combining our efforts also into a number of open source packages which are named here, libraries, and other tools which are sitting a little bit above that software stack. I'll go into that later on with a bit more detail. And what we actually want is to simplify the AI approach, obviously tame the data. That means really get insights out of data instead of just handling the data. We want to deploy it anywhere. That's also an important thing because like you see in ImplantNet, you do the training on a big data center, but you run the inference on a mobile, right? So we need to support this way, and it's often the case that AI is actually an end-to-end problem. It's not a data center problem by its own, as many of us think sometimes. If you focus on the data center as an old HPC guy, no, there's a lot of things happening on the edge as well. Drones take pictures, you can do pre-selections there. The steering of the drone alone is also something which you can support by AI. And we want to scale it, right? Like we've seen in the examples before, using 128 machines or up. We had over 1,000 machines in the PlantNet example, as described by Gabriel before. So we want to scale it as well. So let's look into details here. If we look into the hardware, we often think about the processing hardware here, right? CPUs and accelerators. That is obviously important, but it's not the only thing which is important. We need to handle a lot of data, and we need to move the data around. So we need to store it. So we have some technology here. We need to move it around on cluster level within the machines, and we also need to move it in and out, right? So this can cost a lot of time if you don't have the right hardware for it and the right setup. If you only focus on the processing side, that might not be enough, right? And you need to store a lot of data as well, which needs to be readily accessible. We're building a lot of technology around that with the current and the next generation of our Xeon processor and the storage technology here. So we'll go into more detail into these sections right now. So if you look just at the hardware, right, there's two dimensions here. One dimension is where do I need to have this hardware perform which job, right? So do I have it in the cloud, basically in the data center? Multi-cloud basically means hybrid cloud, so you can have it on-premise, off-premise, whatever you prefer. Then on the edge and in the device, right? In the device, for instance, I need to go low on power usually because they often operate on batteries like drones or cameras, which are portable. And then on the edge, I'm somewhere in between. It's not in a data center, but I probably have more capability there from a compute perspective. So the PlantNet example or a flying drone are good examples for an end-to-end, right? Because you have some AI in the device, you do a data concentration in a gateway, and then you do analysis on the back end, or sometimes just the training on the back end, run all the inference on those two devices or edge compute machines. So that's one dimension. The other dimension is, and we heard this today and also in my example, you can use generic hardware. You can use what you have in all your data centers, which we are familiar with, the clusters which are built on Xeon processors and general data center technology. You can do that. On the other hand, we hear a lot about accelerators, right, who are doing specific acceleration for specific parts of a solution, right? Now, what is best, right? That's the question. Our answer to that is one size doesn't fit all. You might be really, really happy with just a solution which is built on standard hardware, right? Xeons in a data center and some other technology in clients like Atom and Core. Fine, that can work very, very well. And actually, we think that most people who are using AI today are really well off to use just Xeons in a data center and normal PCs out there in the field. But if you have very intensive workloads, you might ask, okay, can I use acceleration because of my workload, 80% is on training. So, hey, can I build something which runs this very well? So our answer is, let's do both and have accelerators for both dedicated deep learning training, dedicated vision inference, for instance, in those devices, dedicated deep learning inference if you really run a lot of inference as well. So we're building these accelerators. Movidius is existing, the Nirvana neural network processors here, the NNPL and NNPI for learning and inference. They are in development, and we expect them in the second half of 2019, right? So you can't have them right now, but we are developing those. And then there's other special hardware or steps in between. You can use FPGAs as something which is between a very specialized piece of hardware and something which is very generic, right? FPGAs, for instance, can be used very well if you run inference in a data center and you have real-time requirements, low power requirements, and your inference is usually of one type and you don't change the model that often, right, then FPGAs can be good. And then there's very specialized areas like automated driving, autonomous driving, where you have special requirements on the whole solution set. And here we have, for instance, Mobileye, which is an Intel company, which is building very specialized solutions for automated driving. So we try to offer a range of hardware because we don't think everything fits one piece of hardware if you want to have an optimized solution. But you can start with generic hardware, for sure, right? And then you can scale up if you really have the need to go very intensive training or very intensive inference or have edge device needs. So that's the overview of the hardware. I don't talk so much about Xeon. My colleague will do that Sean, on Wednesday, I think, right? So I talk a little bit about the special hardware here to a certain extent. So the NNP, the Nirvana Neural Network Processor, we have two types of those in development. Again, comes in the second half of 2019. One is for training. So what we want to do with that is really build a special part of hardware which is really tailored to all the operations you need to do for training. Period. Nothing else, nothing less. So it will run this very fast because of high parallelism, fast memory access, and other features we build into this architecture. So it's a complete new architecture, just built for that. And then on the other side, if you have very high inference requirements in terms of performance, you can build accelerators there, right? Which you can put into appliances, but also put it into a data center, right? This is what we do with the NNPI. So the architectures are different, right? We call them Nirvana Neural Network Processors because they all handle neural networks, right? One training, the other inference, right? Again, in the cases when you need this acceleration. For many people, a Xeon-based solution, core-based solution will be very sufficient. But we are building those parts that you can have also accelerated workloads run very well on this setup. Okay, now one other thing I wanted to mention, which often is forgotten if we talk about processing, right, is how can we handle the data? Now, this is the well-known storage hierarchy which we had for a long, long time, right? We either have things on a tape or a spindling hard disk. The warmer tier of data is on a solid-state drive, and then what is hottest, right, what I need to really manipulate a lot, I put into DRAM. And then I can, depending on my application range, I put more here or more here or more here, right, to reflect that application. Now, with new technology which we are building, and we have been talking about this since a while, now it's becoming reality, we can actually update this storage hierarchy. And this is obviously independent from AI, but I thought this is important because what we need to do in AI is we need to handle a lot of data, right? If we make it faster, and make it faster because we introduce new levels into this hierarchy to have faster access at still manageable price and TCO parameters, then we will be better off, right? So what we are doing here is actually using certain technology to build solid-state drive, our Optane technology, to build solid-state drives with higher performance. And we're using similar technology actually to build more or less something which we can use as random access memory, right? In the same way. So this will actually make the handling of data faster. And this is what we need for AI as well. It's not just that we build accelerators. No, we also have to build the data infrastructure in the right way. And this is our approach to do that. Again, on Wednesday, you will hear a lot more about this as well. Now, that was the hardware piece. And frankly, I think equally important here, we often don't think about this as when we look into hardware, we're fascinated about it. But the software is really making a difference here. And I'm not speaking about the application software layer yet. I'm speaking of what you would call maybe middleware, right? So here you are, basically, if you're in deep learning, you've heard about TensorFlow, MXNet, we've seen that before in the examples. So what is below that and what is above that from a software perspective, and how are we involved? Below that, what we need to do is to make sure whatever comes out of these frameworks for training and inferencing or for traditional machine learning here runs very efficiently. And it's not enough to build the right hardware. It's also very, very necessary to optimize the software. So what we, for instance, have done, we have invested a lot of work here into the math kernel library for DNNs, and also direct optimizations into those frameworks to make things run on generic hardware. And we have seen a lot of speed up. So if you have tried running deep learning training, deep learning inference on CPUs 2 years back or 1.5 years, do it again, and you will see a lot of speed up just from the software running on the same hardware, right? Let alone on the improvements we made on the hardware. Now, there's a few other things here, Python and DAL for machine learning support, and there's another thing which we call the ngraph compiler, which is actually targeted to make this optimization here, which can be quite intensive to optimize different kind of frameworks on different kinds of hardware. You have lots of combinations. How can you make this easier? That is the approach we have with the ngraph compiler, to really look at a layer these frameworks have in common and put kind of hardware stubs below that to make this optimization easier. That's the approach we have in the ngraph. This is open source here, right? So you can look at that. It's in beta right now. And this is for the optimization. So we invest a lot of work into this, either direct optimization or by the ngraph compiler, to make things work faster. Now, we go also beyond that, right? And I've just brought up 2 examples here. The OpenWino toolkit is actually focused on making inference better. So assume you have trained your neural network. Now you want to deploy it on different platforms. You might think that's easy. Well, yes, it is to a certain thing, but if you want to optimize it, if you want to optimize the model for certain hardware, if you want to do quantization and other things right, then you can use OpenWino. So this is a tool which I would place a little bit beyond what you get out of the framework. And then we also just released into open source Norta, which is basically an open source deep learning platform, which supports certain steps you need to do to really run training and the training work cycle easier in a Kubernetes environment, frankly. So you might want to have a look at those things. You can come to us later, or basically look it up on the web, and you will see more details about the things we're doing. But I just wanted to give you a little bit of an overview of the software investment we have, which is very, very important in the world of AI. Now let's look at one more thing, right? Which I think is important, the optimizations of the deep learning frameworks. I've told you, if you tried this 2 years back, try it again, because we have done all of these optimizations, and we have done optimizations on different levels. On the scaling level, on basically scaling out on the core, not just on the machine, on vectorization, parallelization here, and efficient memory usage with certain technologies which we have here, like high vector efficiency, use MPI, and all the things which we know very well from the HPC world, bring it to the AI world so that we have really optimized frameworks on all of the platforms we offer. Up and foremost, obviously, the standard hardware which you have to enable you to really do the AI where you have your data already, which is in the data center, for instance, or in the client side. So we are optimizing these frameworks, right? Obviously, you can't do everything in parallel, so we're focusing on the most well-known and well-used frameworks, but we're also gradually going to other frameworks as well. If you want to know more, right, and also install the latest and greatest, which I recommend to you to get the optimal performance, you can go to this website here, Framework Optimizations, and you will get all the background on how to do that. I think it's important to really make sure you have the most optimized frameworks in place because that will give you performance and give performance to your end users you might serve with your data centers. Okay, so then I've talked a little bit about the technology, hardware, software. So what is behind that? I didn't want to bring too many benchmarks here, right? If you're interested in those, we can talk later. But I wanted to show you a little bit of the effect we see from software improvements plus hardware improvements. Now, this diagram looks at basically comparing our current product with our forthcoming Xeon Scalable product. When you use the same hardware here and use different kind of data types, int8 for inferencing, right? You can already get up a factor of 5. That's basically a software method alone, right? It's a little bit different to the optimizations I was referring before, but it's a data type optimization for inferencing. You reduce the resolution, you get higher performance. But you need to, and you can support this in hardware, and this is what we have done here with the vectoral neural network instructions, VNNI, in what we call the DL boost. That's the marketing name for that. And you can get another factor of 2 just with this improvement, right? You don't change the software from this step to this step. This is a hardware improvement. This was a software improvement, right? Just to show you that. And this is projected performance, right? That part isn't out yet. So we will see what the reality will bring. But this is what we have projected, and it's already very, very promising. This is to show you that we're improving general purpose hardware. We're not just building accelerators, we're also improving the general purpose hardware to run AI applications better. Okay, so a little bit on the software side, we have Norta. I talked very, very quickly about this before, though this is basically a tool in the open source to build, to make the cycle of building, training, and evaluation easier. If you're interested in that, you can go to GitHub and download it. It's in beta right now. And one more thing, right, we've talked about before is community. So hardware, software, community. What we mean by community is various things where we partner with other companies. We have a program called AI Builder where we do this, where you can actually look at solution blueprints and look at partners which you might want to have from a hardware, software, integration purpose to help your solution, right? And then for the developers amongst you, I recommend to go to the AI Academy where you can have not only the software for download, but also look at training courses around AI on best known methods in exchange in terms of what we call the developer cloud, where best known methods are exchanged. So this is our contribution to the community part, which is equally important, and I invite you to look at these various places where you can get support for really building your solution. Now, one last example I have before I end. which is a training example which we've done together with a company called Novartis, which you probably know, here out of Switzerland, in a different part of Switzerland, the German-speaking part. There's a pharma company. They have the concrete problem of training a method, right, where they can actually take pictures of cells and see the effects of a new substance on those cells. They call this high content screening. High because it's very high resolution pictures here. And they had the concrete problem of fitting this data into certain other architectures, right? And really fit the whole picture, because they couldn't just use lower resolution pictures like in the ImageNet example, and they couldn't divide up those pictures either, because they lose fidelity by that. If you chop the picture here, you will lose the fidelity and not see this anymore, right? So, hey, what did they do? They did two things. They used the Xeon machine to fit all of these pictures into memory to make it faster, and then they also scaled it up, so they used, instead of one machine, 8 machines, and then they had a sufficient setup to really do this training with high accuracy in a manageable time of 3 to 4 hours, right? So, nice example. If you want to know more about this, come see me later on. I can give you a little bit more details around that, but I found this is a very nice example to show you what we can do with CPU-based training today. Okay, with that, I'm at the end of my presentation. I get the oversign here. I'm just on time, as it seems. So if you want to simplify, if you want to speed up your development, deploy AI anywhere, come and partner with us. And I hope I gave you a little bit of an overview with some practical examples how you come to real solution, how you come to real insight using AI. Thank you.